Hello everybody. So there was a requested video on detailing of IS 13920 for every elements like beam, column and the joints. So for that, before going to the detailing, I want to go step by step. So in this video, first I will do the load calculation of frame building. Okay, that is like a residential building or any RCC building. Okay, beam column system building. So first I will do the load calculation in this video. After load calculation, in the next video I will tell you how to analyze the structure. Okay, that is the structure analysis. In this video we are going to calculate the vertical load and the horizontal load. So vertical load is dead load and live load. Okay, so vertical load we will calculate. Under vertical load we will calculate the dead load, okay, and the live load. And under lateral load or the horizontal load, we are going to we have actually two types like earthquake, okay, earthquake load and wind load. So I'll be going through the earthquake load because we'll be using ductile detailing, so we will calculate the earthquake load. So in this video we are going to calculate dead load, live load and earthquake load in a frame building. Okay, in the next video, so after load calculation we will go for the structural analysis. Okay, that means we are going to find the moment and shear in each member. Okay, each member due to this load, this vertical load and lateral load. Okay, after structure analysis we are going for design. So in this design we will be calculating the amount of steel required. Okay, once you know how much steel is required, then at the end we are going for detailing. Okay, so for detailing part we have to refer IS 13920 for ductile detailing. So this is the whole step. So first part in this video we are going to calculate the load. Okay, so let me take an example of a building which is a two-storied. So the plan I'm drawing, if this is the plan, okay, so like 4 rooms we have, each I have taken 5 meter, okay, center to center. So if I'm going to draw the elevation, this is the ground level, this is the elevation. So I'm having here columns. So I'm having 6 columns. So let me take the size as 400 cross 500 mm. Okay, this is first we have to assume the sizes. Then as per the force, if we need to reduce or increase, it depends on the forces coming to the structures. So this is depend on their experience also, starting how you are assuming the sections. But nowadays all softwares they are using, so for hand calculation it is very difficult as the story heights and buildings are increasing. So but if you use a software you can redesign many times, right? Now, so let these columns are connected by beams. Okay, so there are beams. connecting all the columns. 1 2 3 4 5 6 7. So we have 12 beams. So here also let me take as 400 mm into 600 mm. Okay, so this is the depth, this is the width. Mm depth, and this is the width, 400 mm. So column of, so in plan if you see the column 400 cross 500. Okay, rectangular shape I have taken. So this is the initial approximation of the sizes of the beam and column. And story height, let's take 3 meter, and we may have a parapet of 1.2 meter height. Okay, so this is our roof level. So ground, and this is G+1. Okay, so this is the story. Elevation. Okay, now so let's calculate first how the load comes. First load comes to the slab, from slab to beam, beam to the column. So first we'll calculate the load in slab. Okay, in slabs. So first the dead load. So dead load, or we can say the self weight. So 25 is your unit weight of concrete into, let me assume slab as 150 mm thickness, 150 mm thick. So there will be a slab at this two levels, right? So 25 into thickness 0.15, because this is mm, so this is 25 is kilonewton per meter cube into meter. So we get 3.75 kilonewton per meter square. Okay. Under live load, so if you see for IS 875 part 2, we have live loads for normal residential buildings. We have to take 2 kilonewton per meter square. Okay, this is given in IS 875 part 2. If and at roof, if there is access, like you can go to the roof, we have to provide 1.5. So for roof it is different, 1.5 we have to provide, and for other rooms we have to provide 2 kilonewton per meter square. So I have taken 2 kilonewton per meter square, and we will also have floor finish. Okay, I'm going to add here also floor finish. So let me add floor finish as 1 kilonewton per meter square. Okay, so live load I'll take 2 plus 1, 3 kilonewton per meter square. Okay, this is our slab dead load and live load. Now next, calculate for beam. So beam dead load is, so I have taken here only one slab and here also one beam. So 25 is kilonewton per meter is unit weight into the area. So 0.4 into 0.6. So we get 6 kilonewton per meter. Okay. Now coming to the live load. So live load will come from the slab. Okay. Now from the slab, if you see, this is a slab, and then there are beams all around, right, with the columns at the ends. So if it is a two-way slab, this is the way there is load transfer. So at angle 45 degree. Okay, that means if we consider this beam, for this beam, this is the amount of load will come. That is, the total load here is 3 plus 3.75. Total load is dead loss plus live load, 3.75 plus 3, this plus this. So we have 6.75 kilonewton per meter square. So this into, we have to multiply the area. Okay. And for this beam, again, you have to multiply this triangular load. This is how the load from slab transfers to the beam. If it is a one-way slab, that means your length is twice of the width, then the load will be transferred half to here, to this beam half, and half to the other beam. So only to this beam and this beam it will transfer. Okay, if it is a one-way slab. And if it is a two-way slab, like this, transfer of load from slab to beam. So now 6.75 is the load. So if I take this beam, now the length is equal, right? Both sides it is equal in our case. Because it is equal, so all the four beams will take equally. Or you can also calculate using this 45 degree, you will find our, so if this is a slab, this is 5 meter, so 45 degree means your, this will come at 2.5, half. Okay, it will come some like this. So all will get equally. So I'll directly multiply the load, 6.75 load, into total area is 5 into 5 by 4, because 4 beams will get divided, so each beam will get by 4. So how much? 6.75 into 5 into 5 divided by 4. So you are getting 42.1875. This much kilonewton, right? Now in beam it will transfer as kilonewton per meter, because 5 meter length. So the live load will be this, again you have to divide by 5 meter length, because 5 meter span of the beam is there. So your live load will come 42.1875 by 5. So 8.44 kilonewton per meter. Okay, so your dead load is 6 kilonewton per meter and live load is 8.4 kilonewton per meter for the beam. Next we have column. So if you see the column, we have dead load as 25 into, again the area of the column, 0.4 into 0.5, and the height of the column is this elevation height 3 meter, okay, into 3 I'll put. So you get 15 kilonewton. Okay, this is for the column dead load. Now we also will have a brick wall. Okay, so I'm going to add, because this is a beam column system and this openings will be filled by the brick, although we'll be also having the windows, and doors, but I'm not going to reduce for that. So let me fill all these areas, that the spaces between the beam column, as brick wall. Okay, so next is our brick wall. So brick wall load will be, let me take 20, because this is not RCC. So 20, I'm taking unit weight, kilonewton per meter cube, into, if I'm assuming as 230 mm. Okay, the width or thickness of the brick wall, 230 mm of wall I'm putting all around. So 20 into the thickness is 0.3, and the height is 3 meter. Okay, the elevation height, brick infill we say. We are filling the space of this area with brick. Okay, so 0.3 into thickness, and we have to multiply the length. So how much length will be? If so, all around, if I'm going to put, so this is 10 meter. Okay, 5 plus 5, 10 meter in this section. Again this 10 meter in this section, and 10 here. So all around, if I'm putting, we have 60, 30 in x direction 30 meter, and y direction 30 meter. So I'm multiplying 60 meter. Okay, so we get as 828 kilonewton. Okay, so this is, we have calculated the dead load and live load. Next we are going to calculate the earthquake load. Okay, so if I draw this frame again here, so if these are the beams, so we have got, for the beams, dead load is 6 and live load is 8.44. So let me write this 8.44 kilonewton per meter. Okay, next we are going to calculate the earthquake load, lateral load. Okay, so we will be calculating the forces in this 2-story at the roof, at the floor level. Okay, so first we have to calculate the seismic weight of the building. So to calculate the seismic weight of the building, we have to calculate the total load per floor. Okay, so let me take first at this level. Okay, so I'll put as first story, and this I'll put as roof. Okay, so at first story, so total load means here when we are calculating, this is to calculate seismic weight of the building. Okay, so in order to calculate the seismic weight of the building, seismic weight contains dead load plus live load, okay, of every members. Now for the live load, if you refer table 8, it has given that if your live load is up to and including 3 kilonewton meter square, you can reduce the live load to 25%. If it is above 3, you have to reduce 50%. So here reduction, so this is table 2 of IS 1893 part 1 2012. Okay, 2002. So reduction in live load for our case, because our load in slab we have considered 2 kilonewton per meter square, so it is less than 3. So our reduction in live load is 25%. So we'll be taking for seismic weight of building calculation 25% of the live load. Okay. So now we are going to add slab weight plus beam plus column plus the brick wall. Okay. So now slab, dead load plus live load we are going to add. So how many slabs are there if you see? Here, 1, 2, 3, 4 slabs. 4 slabs, and the area is 5 into 5 because we have taken all diamonds same, 5 into 5. And what is the dead load? We have 3.75 and live load we have 3. So we will take 3.75 plus 25% of 3. Okay. So for the slab, 4 number of slabs, area is 5 into 5 because we are going to calculate total load in each floor. For the first floor, so we have 4 slabs, area into load is, dead load is 3.75 plus 25%, 25 by 100 or 0.25 of 3. 3 is our live load. This is live load, this is dead load in the slab. Okay. Now this was for slab. Plus then beam. So we have 12 beams. Okay. We have taken 12 number of beams, each of 5 meter length, and the size is 400 cross 600. So we have 12 beams, 5 meter length, and this. Your dead load is 6 and live load is 8.44. So again same. You'll see all we have calculated in kilonewton. This unit is coming kilonewton for beam also. So 12 number of beams, each of 5 meter length, into your dead load 6 plus 25% of live load 8.44. Okay. So this we have taken for beams. Now we are going to calculate for columns. So how many columns we have? We have 9 columns. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 9 columns. So 9 columns, each column dead load is 15. Okay. 15 plus then we have brick walls. Now if you see here in the dead load we have taken 3 meter. When we are considering the seismic weight for the first story, the 3 meter is from this. Okay. This is what we are considering, from center of the column to the center of the story, first story and second story. This 3 meter. So the upper story, if it is, there is 3 story, again 3 meter. But since we don't have the upper stories, for the roof level we have to only consider 1.5, 3 divided by 2. Okay. For brick wall similarly we have 828 because this total we have taken already, not, so I'll add total 828. So if you add all this, so at the first story we are getting 1900 kilonewton. Okay, seismic weight. At the first story total load is 1900 kilonewton. Next, at roof level, so we have same slab for all 4 slab will come at roof level also. So if you calculate for the slab, the value will come 450. That means this value. Okay. So I'm adding the same 450 plus we have beams will also come to the roof. So I'm going to add 486.6 because this 1900 is 450 from the slab. Then for beam it is 486.6 plus for column we have 15 into 9 which is 135 plus for brick we have 828. Okay, so 486.6 plus for the columns because half is going above, so I'll just put half 135 by 2 plus we have this, we don't have brick wall, so I'm not going to put brick wall, I'm going to add parapet. Okay, so parapet of 1.2 meter all around the building. So 1.2 meter is the height into 25 is the unit weight, and if I'm taking 150 mm thick, okay, thick of parapet into the length. What is the length? Length means because our parapet will come only at the boundary, right? Boundary of the building at the roof level. So that means it's a perimeter. So perimeter means 10, 20, 30, 40. 40 meter. So I'll multiply 40 meter here. Okay. So at roof level we have got, adding all this, 1184 kilometer. So we have ground level, then we have G+1 and then roof level. So what is the height? Ground level if I take at 0 meter, that means this, I am taking this as G, this is G+1 and this is roof level. Okay, 0 meter, then we have 3 meter height here and we have 6 meter at roof level. Okay, so the seismic weight W, this is height. Okay, HT I have written, so this is height. Okay, height. So at seismic weight we have got at roof level 1184 and at ground level we have got 1900. Okay. So total, if I do, total seismic weight of the building is 3084 kilonewton. So W is our seismic weight of building. That is total dead load and live load. Then we have to multiply WH square. That means 1184 into 6. 6 meters is H. So this height is H. 1184 into 6 square, we got 42624. So and here 1900 into 3 square is 17100. Okay. After that we have to calculate the force. Okay. Before calculating the force, we have to calculate the VV. If you refer clause 7.5.3, VV is your base shear, which is equal to AH into W. W is your seismic weight. So now first we know the seismic weight 3084. Okay. Now we have to calculate our this coefficient, seismic coefficient AH. So your AH formula is Z by 2 into I by R, it is there in the code, SA by G. So this is, now we have to refer zone value. So depending on the zone, this Z value depends, and this is how this from AH your earthquake load also varies, and your design will also vary, because if your earthquake load is more, earthquake force is more, then because there are different load combination, your earthquake load combination might come more dominating. So for that you have to design. So that's what the zone factor or the different zone, seismic zone depends or affects the design here. So let me just here assume. So depending upon the zone that you are considering, your Z factor will come. I'm assuming that it's in zone, the building is in zone 4. Okay, so if it is a zone 4, your Z value is 0.16. Okay, so by 2. So this Z factor you can refer table 2 in same IS 1893 code. All your earthquake design you have to refer IS 1893 part 1. So 0.16 by 2 divided by I impedance factor. So here impedance factor is 1. This also you can refer the code. If it is like hospital, your impedance will be more. So for that your factor will be different. Then response factor R I am taking because this is we are designing for SMRF building. Okay. Because ductile detailing we will take spatial moment frame, moment resisting frame. Okay, spatial moment resisting frame. If you refer table 7, you will get this response reduction factor. So this is 5 for SMRF building. If ordinary moment resisting frame, it is 3 into 5 by SA by G. Now SA by G you have to refer figure 2. Okay, figure 2 you have to refer. For that you have to calculate the time period. So if you go to clause number 7.6.2, you will get the time period formula as 0.09 root over into H root over D. So if you refer the code of 2002 version, you will see this H is not there. They have forgotten or there is some misplace. H is not there. But if you just read it down, they have mentioned that H is the height of building. Like this is the time period where H is the height of building. Like this they have written. So H they have actually printing problem is that. So 0.09 into H by root D. So for this building our time period is 0.09 into height of the building is, you see, 6 meter, plus we have 1.2 of parapet. So total height of building will come 7.2. Okay, that means 6 meter is the height of the building plus parapet height is 1.2 meter. 7.2 by root over of your plan length. Okay, x direction, y direction will be different, that's why. For us same it is 10 meter, the plan, this dimension. Okay, this is our D, 10 meter. So calculating this, our time period is 0.2 second. Okay, for this T, if you refer the figure 2, you will see SAG value for time. So SAG value referring figure 2 for 0.2 second. Okay. So I'm looking into the code. So we have like type 1, type 2, type 3 different rock soil. SA by G is the spectral acceleration coefficient. So because our time period is just 0.2, so we'll get same for both all the 3 soils, but it may differ. So let me assume that we have medium type of soil. So our SA by G for 0.2 second for medium type soil, if you refer figure 2 from the plot, or also there is, like, they have already given the value in clause 6.4.5. okay, you can refer also clause 6.45. so SA by G, if you see, if the time period is for medium soil 0.1 to 0.55, within that, less than 0.55, your SA by G is 2.5. So I'm going to put 2.5, or you can refer figure also. Okay, directly values also you can take. So your AH value is, after multiplying, so 0.16 by 2 into 1 by 5 into 2.5. So we are getting 0.04. Okay. So next is your base shear VB. So VB is, here we have taken H into W, so 0.04 into W is 3084. So we will get 123.36 kilonewton. Okay. So coming to the force is your base shear into, at any story if you are taking, into your WH square, okay, this WH square by summation of WH square. So if I add both this, 42624 plus 17100, I get 59724. Okay. So for F1, okay, for the F1 I'm going to take this, and F2 I'm taking at roof level. So for F1 we have VB is 123.36 into WH square is 17100 by 59724. Okay. F2 is 123.36 into 42624 by 59724. So calculating, we get 35.32 kilonewton, and this will be 123.36 into 42624 divided by 59724. 88.04. So if you add both this F1 and F2, total base shear you will get at the bottom is 123.36. So this is how we are distributing the base shear at every story. Okay. So we got 35.32 here, lateral load we have to design for this, and above we have got 88.04 kilometer. That means base shear VB is here. Okay, total base shear. Now this base shear has been distributed at both the story. So now we have got our framing building. We know the vertical load, we know the lateral load. So in the next video we are going to analyze the structure and calculate the forces in the beam. Okay, in the beam, what is the moment, what is the shear force due to this vertical and lateral load, and also for the column and beam, because beam and column system, right? For the slab, because framing system is beam column system we say, so we are going to analyze beam column system. For the slab, we have, like we already know that the load. So for the load, if when you know, you can design this, because if it is a two-way, you can design the moment you can use as alpha WLX square, right? For the two-way, where alpha is a coefficient. For in our case, the slab, if you are looking at, the slab is 2H discontinuous and 2H continuous. For that, you have to take the coefficient, and the load is we have calculated 6.75 into the length. The length is 5 square. So you know the moment. Then after moment, you can design. You can calculate the steel for the moment. If you are like the AST. Okay. So for the slab, I'm not going to design. We are going to design for beam column system only, because it is easy, and this is a so the steps I have already said you. Just you have to calculate the moment, alpha WLX square, put the coefficient depending on the age, continuous or discontinuous, the factor, then the W, which we have already calculated, and the length. So once you know the moment, you can calculate the area of steel. Okay. You can also refer the roof slab that I have designed in water tank. You can refer that video also if you want to go into details into this design. And if it is a one-way slab, then for one-way slab you have to design like a beam. Okay, if it is a one-way slab, so your edge, now this is like a simply supported WL square by 8. You can put the steel as per this. Okay, so you can provide the steel. So in the next video, we will be analyzing this structure, this framing building. Okay, thank you for watching. Hope this video was useful to you.